3D reservoir modeling and data integration. So this is our subject. Okay, so we have to know what is reservoir, what is modeling, okay, what kind of data we need, and how we are going to integrate to each other. So you see, we are talking about seismic and petrophysics. And we are saying that the geophysicists using some logs, okay, like sonic log is directly related to the seismic. So these data, okay, different disciplines, petrophysics, geophysics, geology, all has to be integrated together. So geomodelers are getting data and information from different disciplines, okay? So today we are gonna define the workflow, how we are gonna work, okay? What kind of data we are gonna get. Then what's happening in the field, okay, currently, because the world is changing. Now there are lots of sensors installed in the field and they are acquiring data every other minute. So there's a huge data already gathered, okay? So what are we gonna do with this data and how we are going to use it in our model? And then what are the challenges? How we are going to solve them? And for doing the modeling, what kind of tools do we have to have? And those tools, how we are gonna use them? Okay, these are the issues today. We are going to little bit touch each of them. Okay, geological modeling. I asked at least 10 of you, and I got only a couple of the answers. The rest doesn't have any idea about what's geological modeling. So here is the definition. It says geological modeling is the applied multidisciplinary science of creating computerized representations of hydrocarbon reservoir for dynamic simulation. So we have what we are doing in geological modeling, we are creating a computerized representation of the real reservoir, hydrocarbon reservoir, inside the computer with the dimensions, okay, XYZ coordinates all over the reservoir, not part of it. We have to cover comprehensively not only hydrocarbon but also the aquifer, okay, the water area, because we are gonna, when we start producing, we will produce some water, and we will get water also influence in the reservoir. So that's why we have to include the water area, water zone. So all these physically, okay, we have to get their XYZ coordinates of each part of the reservoir inside the model. Not only physical, okay, physics is not enough. You might have the physics represented in the computer program, but what is in it, okay? What is the rock quality? And what is the porosity, what is the permeability inside that rock, which is going to influence your flow behavior. So you have to have both physics and also the rock property, which is geology, okay? And when I say the physics, which means the top structure, the faults, all these things, which is geophysics, okay? When I say the porosity, permeability, which is the petrophysics, okay, calculated and measured by the logs, all has to get together to generate computerized representation. And then what is the end product? So we do, let's say that, okay, we have done a perfect model. It includes the physics and it includes the rock property. Everything is perfectly now available in the model. What do we do with that? So we have to give it to the reservoir engineer for dynamic simulation. So our part is modeling and their part is simulation, and their part is dynamic, our part is static. Okay, so static versus dynamic simulation. So when I say dynamic simulation, what does it mean? It means that all the wells drilled has to produce, right? It's going to produce hydrocarbon, either gas, natural gas, or crude oil. And this crude oil or gas is going to be associated with kind of other liquids like water, because in all the reservoirs we have water. So by water coning and water encroachment, so we are going to get, together with hydrocarbon, some water. So the simulation, by the time step, every day or daily, weekly or monthly, they are going to show how much oil or gas or water is coming from certain wells. So that's the dynamic simulation. So we are serving, by doing geological modeling, we are serving to the reservoir engineers for simulation. So before we do the geological modeling, we need the geophysics working on the seismic. And then we need petrophysicists working on the log. And we need geologists working on the rock. So we collect all this data, integrate inside the model, and give it to the reservoir engineers. Okay, so this is the workflow. So we start with the seismic data. Okay, seismic interpretation has to come. Then during the seismic interpretation, as you may know, the seismic data is recorded in time. Okay, if you know the seismic process, when they acquire the data, they make some kind of artificial noise, either by explosion or by hammer to the ground, and then it is recorded in time domain, then has to be converted to the depth, because we are dealing subsurface. Subsurface means XYZ coordinates in the subsurface. Okay, so all the seismic data has to be converted to the depth domain. Then we have the well data. We build the well correlation, okay, between the wells, from well to well, how the rock properties, and where does the reservoir start, where does it end. Then we go to facies modeling, okay, which is the rock quality distribution around the reservoirs. Then property modeling, which is porosity, permeability. And then after you finish this cycle, you can go well design, okay, for the future wells. Where do you have to drill? You can locate the well and tell the drilling engineers and reservoir engineers, this is the location, best location for the objective, and this is the rock quality, this is the depth where you are going to enter to the reservoir, and so forth. Then production data analysis. All the data up to here is static data. Production data is dynamic, because you are producing, it is flowing. That's the dynamic data, and you have to include in your modeling steps. Okay, that's the integration with the dynamic data. Then you finish everything, you included the production data. What is next? So you analyze your data and check your model if it is predicting correctly or not. Of course, it's impossible to predict 100% correctly, accurately. So your new coming data will show some kind of discrepancy. So you have to go back again to your seismic depth well. So it's a ongoing work cycle, never finishes. From the day one, even day 0, even day -10, before you go to the field, before you do anything, which is called green field, there is no data at all, you have to start modeling, okay, which is called basin modeling. So you have to analyze if it is worth to explore the area. So that's the exploration phase. Then after first well, you start gathering the data. So modeling would would serve all the purpose of exploration, production, field development, enhanced oil recovery, and so forth. So all the phases, you have to be there with modeling and supporting the operations in the field. So we said, okay, these are the steps, but specifically, what are the steps in the model? Okay, inside the model, when you are doing geological modeling, first you have to gather the data, and you have to gather the data from other disciplines. So you have to be talking with different discipline people, such as geophysicists, petrophysicists, sedimentologists, geologists. Okay, so they are going to provide you their data. One type of data is the well data. So you have to put the logs, core data together and correlate one well to another well. Okay, so you have to get the seismic faults. You have to generate the fault data. Then called pillar gridding, which is the squares you generate inside the model. Then you generate the zones, because your log shows that, okay, at the top of the reservoir, it is relatively porous, but as you enter, you are getting much better area, so you have to separate, which is called subzonation. Then layering. You have to divide your subzones into small layers because of your resolution, your log resolution, your core resolution is giving you information every other foot. That's why your layers has to cover heterogeneity. Okay, then it starts with the property modeling. This at the top layer is the structural modeling, and the base layer here, baseline, shows the property modeling. You divide the facies, you do the facies modeling, petrophysical modeling. After you finish the identification of the porosity permeability distribution, then you do your saturation modeling, and then you can calculate your volumetrics. Okay, inside your volumetrics, inside your reservoir, how much oil you have, how much gas you have. Okay, this is what you have to define. Initial oil in place, initial gas in place, for the further development decisions of your managers. Okay, managers are wondering how much oil do they have to invest more. So that's what you calculate. Then, of course, the continuation of the operations by plotting a lot of maps, a lot of data. You have to analyze your data and show your managers, okay, where do they lay out and how do they lay out, and where this is the step where the data analytics comes into picture. Okay, data analytics, that's very important. You have to know what type of data, how you are going to display. Even in this slide, okay, there are certain data I'm displaying in a certain way, such as you see here, well to well, I'm displaying the log curves, and on top of log curves, I'm displaying these points. Probably you see that, okay, black points, which is the core data. Okay, and this is one well, and this is second well, and I can compare from well to well how the property are changing. And in one track, I am showing the porosity from log and from core data. In another track of this well, I'm showing the permeability, okay, permeability points. And in another track, I'm showing saturation. So you see, just this part is showing a lot of data, okay, from the wells. And this one is showing the fault locations along with the top structure. Okay, this one is showing how we have divided these reservoirs into subzones and later by layering. You see, these are the data reporting, okay, while you are showing the data features, characteristics of your data, what type of plot, cross plot or well correlation or 2D window, 3D window that you are going to show it, you have to be aware of it. You have to know how you are going to analyze your data, how you are going to report your data. So that's a very important part, okay? And as you may hear, nowadays in the industry, data analytics, data mining, data storage, data issue is getting hot and very hot because there are a lot of electronic devices, machineries for measurements and data acquisition. So all this data coming into the headquarters, we have to know how to analyze them. Otherwise, they are meaningless numbers. Yeah. So we have to show to the managers what the data is talking. Yeah. So that's important part of the geomodeler's work. Huh? So why do we need geological model? Okay. We need geological model to optimize the operations and development. So we have the field, we are going to develop this field, okay? Drill more wells and then produce and then inject some either liquid or gas to maintain the pressure of the reservoir. So there are a lot of operations and we have to optimize. We cannot do blindly, okay? So to be able to optimize and develop your field, you need a model. Before you go to the field and implement whatever your operational decisions, you have to see the consequences of your decisions on the paper, in the computer, by simulating it. By using the model, you have to see if you made the decisions of drilling, where you are going to drill, what kind of rock property you are going to get. Okay, so to optimize the operations, then to integrate all data in common domain. So I have been talking about this, right? Integration. So you are getting data from geophysicists, geologists, petrophysicists, reservoir engineers, production engineers. They are all bringing different data. So to integrate all of them in the common place, which is the geological modeling, you have to have a model. And then to have reservoir model in 3D environment. So if we are working on paper, it is 2D, okay? The papers are 2D plots, but we need 3D visions, okay? We have to analyze the things in 3D because we are running reservoirs in space, which is X, Y, Z coordinates. There is depth, there's X, Y coordinates, okay? So we have to show everything in 3D. That's why we need geological modeling. For simulation, for dynamic simulation, definitely we need a model. Without this model, geological model, they cannot simulate the reservoirs. They cannot show their flow, how it is affecting the pressure and saturation inside the rock. So they need, this is the base, geological modeling. For volumetric evaluation, so we have to calculate at the end how much oil, how much gas, we have it in place, right? So that's why we need a model. What else? For data management, yes, we need the model to see where we have the data, okay, and what kind of data we need, and to generate a database inside the model, we need it, okay? For data management, we need a geological model. To capture the uncertainty. So at the end, our knowledge about the reservoir is limited. For instance, well data, it is limited. We don't have wells everywhere. We don't have seismic covering all entire, okay? Yes, aerially it is covering, but if it is 2D seismic, it is in the certain lines. If it is 3D seismic, then the issue is vertical heterogeneity, because every 30 meters you have one signal of the seismic, and your reservoir sometimes thinner than 30 meters even. So our knowledge, our measurement is limited, okay? That's why there is uncertainty, and our measurement techniques, our tools are also having some kind of errors. Because of these errors, we have uncertainty, and we have to capture, we have to understand how much we are off from the actual reality by these measurements and calculations. So we can consider this uncertainty in our development decisions. So these are why we need, okay, geological modeling. Okay, so let's finish this session, the first session. So we are going to give 10 minutes break right now, okay, and then come back at in 10 minutes, okay? So I'm going to send you another link.